Hey everyone, welcome back to my channel and another new video. We are continuing the data structures algorithms interview preparation bootcamp. We just finished with binary trees. We did the complete 5-hour long questions video. So if you want to solve any binary tree interview question, watch that video. But the playlist link, everything, all the links, code links can be found in the description below. If you're preparing for your interviews, you can check that out. But in this video, we're going to start with heaps. Very important data structure for coding interviews. It's easy, nothing too difficult, very simple, and we'll be making 2 videos. So in this video I'll teach you about heaps, what are heaps, how it works, the benefits, complete theory, complete code, heap sort, priority queue, and custom implementation. So everything from scratch, we will learn everything about heap. And in the next video we'll do a heaps interview questions video. So if you have been following my bootcamp, you know the format I go with. I do a theory video, then I do a questions video. So after that we'll do probably a, I don't know, 5-6 hour long, because heaps is an important topic. There are many important concepts in it, so I'll do that. But after this I believe I'll also add in hash maps, how hash maps work and how hash maps introduction, because heaps and hash maps get questions that use both of these data structures. So I want to make sure I cover both. So, but don't worry, what I would recommend is follow the order in which I have added it in the playlist. It's whatever you need. Okay, that's all you need. So let's learn about heaps in this video. In the next video, we'll do heaps questions and learn about hash maps and all sorts of things. If you haven't already, make sure you like, share, and subscribe. Comment if you like the video, because it will help it reach more people. Join the Learning Public Initiative, share it on socials using hashtag DSA with Kunal. And yeah, let's get started with heaps. Okay, so first I will tell you about why we are using heaps. Then I will tell you about how it works, and then we'll see it in action, like how to make heaps, right? So forget about what is heap or whatever. Just think about why we are learning about heaps. Okay, Kunal, we don't know anything about heaps. That's fine. We will learn about it later, what heaps are, how it works. But first tell us why. Why are we working with heaps? So the simple idea is that whenever you want to get a particular element, a particular item, let's say you want to get some item that follows some sort of a criteria. For example, storing 10 numbers. So the criteria is smallest number. I want to get the smallest number. Okay, that is the criteria. Now, like, Kunal, how are we going to do this? How to do this? So you can store it in an array, and you can search for the element. It will take, you can do like linear search if it's an unsorted array, and you can store it in a tree if you want. Okay, you can do all sorts of things. But the idea is that my main problem, my main concern, my main task, for example, my main task is to get that smallest item. That's my main task. Meaning, I give you 10 numbers. Okay, I'm like, hey, here are 10 numbers. I'll give you first number, then I'll give you second number, then I'll give you third number, you will store it in your data structure. I'll give you fourth number, you store it in your data structure. Give you fifth number, you store it in your data structure. So on and so forth, I give you 10 numbers. Now I'm like, give me the smallest item. So let's see how that works. So here's my whiteboard. And here if I say, let's say I'm storing the numbers in array. Okay, no problem. So I store the number in array. I give the first number 3. Second number I give 8. Third number I give 4. Fourth number I give 19. Then I give 20. Then I give 2. Then I give 36. I give these many numbers, 1, 2, 3, 4, 5, 6, 7. Now the next question is, okay, I have just given you 7 numbers or n numbers. Can you please find the smallest number in all the numbers I have given to you? That is one condition, smallest number. This condition can be anything, but just to simplify the process, I have taken a simple condition. It can also be, give me the maximum number, or it can also be something like, let's say these are, you have done object-oriented programming. So let's say instead of numbers, these are human objects. So you can be like, give me the smallest age or something like that. For simplicity, let's say smallest number is the criteria over here. Please don't worry too much. Okay, think about the criteria. That's the main point over here. So the criteria is, Kunal, give me the smallest number of all the n numbers I have given you. You'll be like, okay, it's in an array, I will just do a linear search. So in O of n, I can give you smallest number. You're like, okay, that's nice, not bad. But the thing is, my main task, what I want this data structure to do, my main task is that I want the conditioned item. So for example, in this case, I want the smallest item as fast as possible. Let's say constant time. Means in just one single step, give me that item. Smallest item. In just one single step. So I give you 10 numbers, I give you 100 numbers. That's fine. You will keep inserting that in a data structure of your choice, whatever you like, linked list, array, or heaps, for example. You don't know about heaps, but we will learn. That's actually the answer, spoiler alert. Give you 100 numbers, okay, you store it in the data structure, okay. Now I ask you, I gave you 100 numbers, right? Give me the smallest number of all of these 100 numbers. That answer, like, okay, this is the smallest number, should be in constant time. No searching required, nothing, in constant time. How can you do that? Now you will be like, okay, Kunal, let's store it in an array only. But every time you insert an element, sort the array. Every time you insert the element, sort the array. So for example, I'll be like, okay, insert 3. So initially it's empty. You'll be like, insert 8. Okay, 8 inserted. Now I'll be like, insert 4. Okay, 4 inserted. But you can see now array has become unsorted. So I will sort it. Like insert 19, okay, added, insert 20, added, insert 2, okay, added, but now it's unsorted, so sorted. Insert 36, added, so on and so forth. Now I'll be like, okay, give me the smallest element. You can now give it in constant time because it's the element at the 0th index. But there's a problem here which is very obvious. Inserting an element is taking O of n time. Why? Because in the worst case scenario, you insert an item, then you have to sort the array or whatever. Or actually not O of n time, O of n log n time. Yeah, O of n log n or O of n squared, whichever sorting algorithm you are using, not O of n. So worst case scenario, you're getting like, you do either merge sort, whatever, and it's taking extra complexity. Okay, so for inserting an item, it's taking, let's say on an average, O of n log n to insert one item. Okay, that's fine. So the answer that you are getting, like Kunal, you said that I'm storing the data structure and the main purpose of data structure is to give me the query, which is the conditioned item, which is smallest item or largest item or whatever the condition is, in constant time. This data structure is doing that. But the problem is that inserting an item is taking a lot of time. Now the question arises, okay, this is fine. So this thing is good. We will try to maintain the smallest item at the 0th, the very first index. That is fine. Can you reduce this? Can you reduce this? Can you maybe make it O of log n? To insert one item, it will take log n time. Can you do that? That's the question. Yes. Answer is heap. Using heaps, you can do it. So now, I believe you are able to understand why we are using heaps. In any question, when you are given condition, like, okay, you are given 12 n number of movie reviews, IMDb movie reviews out of 10, and you have to find the highest movie review at a constant time. So you will store it in a heap. I will show you how the structure is of heap and everything. But yes, okay. That's why we use heap. Anyone asks you why we use heap? Given a condition on a collection of items, like, okay, I give you n items, find me the smallest item, that's the condition, smallest item in constant time. So heaps will be used. O of 1 in constant time, you will be able to get that item. If you want to add new items, it will take log of n. How it will take log of n? You don't know yet. I haven't taught you that. I will teach you. But just know that it will take log of n. How? I will tell you. Okay, so that's very simple. Let's move forward to how heaps work, structure, and why it takes log of n and everything. Okay, so heap structure. Um, Heap is actually stored in the form of an array only. Like internally it is stored in an array. So it will be stored as an array, but it will be represented as a tree. It will be represented as a tree. For example, what I do is that let's say I insert some items. Let me just show you a dry run. Okay, so here is how it's going to work. I am going to first tell you how the heap data structure is stored. Okay, now the doubt you will have over here is, Kunal, okay, how are you determining that these values are like how when we add, how do you make sure that the smallest item always, or let's say the biggest item always stays in the very first position? We will talk about that later. Okay, right now please don't have these doubts. Right now I am answering the question about the structure of heaps. How is it actually stored? Okay, so here I have skipped 0th index. Let's say I told you in reality it will be stored as like an array in reality, but we will visualize it like a tree. So for simplicity purpose, I have skipped 0th index. Leave it empty. Okay, no problem. So here you can see this is my array in which heap is stored 16, 14, 10, 8, 7, 9, 3, 2, 4. So here you can see 16, 14, 10, 8, 7, 9, 3, 2, 4. Okay, this is, let's say, something called, let's say if the question is I give you n numbers, give me the maximum item in constant time. Here the maximum is 16, you will just return the first element, which is 16, so that is correct. It is true. How it is going to be log of n or whatever when we insert an item, whatever, that we'll look at later. Right now let's look at how it is stored actually. Okay, so in the previous example I told you if someone asks you minimum item, in this example I'm saying if someone asks maximum item. Okay, some of the properties from which what we can see over here. Property number 1 here, it is a complete binary tree. Okay, represented as a complete binary tree. In reality it is stored in array. It is not stored like a tree in reality. But here you can see I have listed down index number 5 has 7. Here also index number 5 has 7 in the tree. So complete binary, you know what a complete binary is? Complete binary is every level is full except for the last level, which is the leaf, and the leaf starts from left to right. So I have 2 here, 4 here, next item will here, then here, then here, then here. Okay, okay, not a problem, not an issue. Okay, complete binary tree. The next thing I want you to notice is that point number 2, every node that you can see here, since this is a maximum heap, a max heap if you will, because we want maximum item in constant time, so it's called max heap. Here you will see every node value is actually greater than, equal to all of its children. For example, 14 will be greater than equal to all the things below it. That is true. Notice something, even though I have the maximum item at the very first index, as you can see over here, maximum item at the very first index, here you will see that this may not be sorted, and that is okay. That is fine, not a problem. My concern is that the first element in the array should be maximum, because that's my main problem. I want the maximum item in constant time. How we will maintain this, I'll tell you later. Okay, now another doubt, Kunal, you are saying it is stored in an array, but how is it represented as a tree? What is the logic behind it? What is the logic behind it? Let's see. So the logic is very simple. Here I can see that the root of the tree is equal to, let's say if we say I is equal to 1. That is true. That is true. Okay, for any root, sorry, not any root, for any node, let's say the parent of that node, let's say if I talk about a node, what is the parent? Parent of a node I is going to be equal to what? You tell me. So let's say if I talk any number. So we talk about index number 5 over here. What is the parent of 5? 2. What is the parent of 4? 2. Okay. What is the parent of 8? 4. What is the parent of 9? 4. Can you see that if the number is I, if the index is I, the parent is I divided by 2. What? 9 divided by 2 is integer number 4 because 4.5, so 4. 8 divided by 2 is 4. 4 is the root. So 4 is the parent. Take any example. Index number 7. 7 divided by 2. Integer value 3. 6 divided by 2. 3. So the parent index of 6 and 7 is going to be equal to 3. These are indices of the arrays, okay, because we are storing it in an array. But how are we representing in a tree? This is how. Parent of every, every index I, the parent is going to be equal to what? I divided by 2. So if I look at the array, I say at index number 6, I have 9. So in this array, who is the parent of index number 6? That's easy. 6 divided by 2, 3. So parent of 9 is 10. And that is true. That's how the tree is represented. Similarly, for any node, what is the left and right? You can figure this out as well. Let's say if I talk about 3. So index number 3 has left equal to 6. Index number 4 has left equal to 8. Index number 2 has left equal to 4. Index number 1 has left equal to 2. So it's just doubling. Left of any index I is equal to 2 into I. What is right? Index number is 2, the what is right? Right is equal to 5. Index is 4, right is equal to 9. Index is 3, right is equal to 7. Okay. So similarly again we have seen the pattern. Right of any index is equal to 2 into I plus 1. Simple. This answers the question of how the tree, how the heap is actually represented. In reality, it will be stored in array. We will read it like a tree. To be more specific, a complete binary tree. And every node will have value greater than equal to all of its children. The maximum item or the minimum item, whatever you need, will always be at the very first index. The rest of the array may not be sorted, but what the rest of the array will have is this condition number 2. Every node greater than equal to all of its children. And how is this array represented in a tree? These rules. Because of this formula, are there any pointers required? Like in, when we have a node class, we have like node next, node left, node right in tree. Is that required now? No, because we are getting the answer directly from formula. No pointers required, that is why. No pointers. Well, Java doesn't have pointers, but you get my point. Pun intended. All right, okay. Now, one more thing left is what is the height of this binary tree? Complete binary tree, what is the height? For n elements, you know this, you have done tree playlist and videos. Log n, okay. Height log of n. Please don't ask me why. I have covered it in detail in the trees video. If you want to learn more about complete binary tree and how the height is log n and anything, please watch that video. Okay, so we learned about the motivation behind heaps. We learned about how heaps will be stored in my program, in my computer, in my data structure, how it is represented. We saw that. So it will be stored in an array, but in reality, we will look at it like a tree. And like traditional tree, it will not have node next, node right, sorry, node left or node right, but we will use this formula to get those parents left and right for every node. That is why these pointers not required. Now, few unanswered questions, some things that you don't know right now, which is, Kunal, when you add a new item, let's say you add in 37. Okay, so in reality 16 should be replaced with 37 because you said max heap. In this example this is max heap, so max heap will always have the highest item at the very first index, and we know that we insert from left to right at the very last level. So let's say for now at index number 10 here I insert 37. Now my heap has become wrong because 37 should come in the place of 16. So Kunal, how would you move this thing up? That's the main question. Question number 1, that's the doubt. Doubt number 2 is that when you have to remove an item, how will the tree restructure? And let's say in this case we are only talking about removing the item at the very first index. That's the whole point, right? If you want to remove anything from the middle or something like that, then just use arrays or normal binary tree. Why using heaps? Only using heaps when you are confident that you are working with a condition. That's what you're going to be working with. So removing item, let's say you have to remove obviously the first item, so the maximum item, just give me the maximum item, remove it. So like, okay Kunal, I will remove this, not a problem, but now this area is empty. Now this is empty. How do I make sure that the next largest element is replaced over here? How do I make sure that happens? These are two questions you may have right now. Okay, so rest everything is clear. Now let's answer these two questions: how to insert and how to delete. Okay, so what I'll do is, let's say I start a new tree, okay, a new heap, and let's say we do min heap now. Min heap means in constant time I need minimum item. So at the very first index we will have minimum item. Let's say at first I insert, this is my array, currently it's empty. Currently it's empty, index number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever. So at first I will insert anything. So let's say I insert 8. So 8 will go over here because nothing is available. So index number 1, 8. Now I insert, let's say I insert 7. So I will insert 7. Now 7 will go, let's say first I will insert, because it's a complete binary tree, so from left I will insert 7 at index number 2. So in reality it is being stored in like an array like this, but this is how we are visualizing it. So I'm writing both the ways so you understand. But now there is a violation because it's a min heap. Minimum item should be at the very top. So we are going to check the item that we have just inserted, check its parent. Is it smaller than the parent? Yes it is. Okay, swap. Let's say I keep inserting, let's say I will insert, so it will be swapped. Let's say I insert 9, 10, 11, 12, 14. So 9, 10, 11, 12, 14. It's fine, condition is maintained. Then 13. That's fine. So you can see it makes sense. This entire array may not be sorted, but this thing is important. First item should be minimum. 13 here, and let's say after that I insert 5. So let me just write this down. 1, 2, 3 index, 4th index, 5 index, 6 index, 7 index, 8 index. Now I insert 5. I insert 5 and it's like, hey, you have just inserted 5, index number 9. That is violating the condition. Violating the condition. So please remember one thing. Here I know that for every node, value of every node is less than equal to all its children. Make sense? So value of 10 is going to be less than, has to be less than all the children. Value of 9 has to be less than all of its children. Value of 8 has to be less than all of its children. Right now because of 5 that is violated, but in general. So I know one thing I want to share is, obviously I'm going to check up, right? If this is violating the condition, then I have to send it up. So I will just check it from up. So is the parent of 5 that I have just inserted, and you can find the parent very easily, n by 2. Is the parent of 5 greater than 5? Yes, it is. Okay, swap. So I will swap it. 5, 10 will be swapped. In reality, it will be like this. Now you'll be like, Kunal, do you have to check it with the other side of, so do I have to check it with 13? Think about it. No, because I know that 13 was actually greater than whatever was over here. So if 5 was smaller than 10, then 5 is automatically going to be smaller than everything that is over here, which is only just 1, because it's complete binary. I think about it now. If I know that, see, in reality, for 10, I know that 13 is greater than 10. Okay, so I'm checking if 5 is less than 10, then of course 5 is also going to be less than 13, hence you don't need to check. Why is 5 going to be less than 13? Because 13 is greater than 10. Makes sense. So I checked, like, okay, I added 5 over here first at index number 9. I'm going to check, hey, is 5 less than 10? Yes, it is. Okay, swap. Now, do I need to check whether 5 is less than 13 or not? No, because I know automatically all the numbers below 10 are already greater than 10. So if 5 is less than 10, obviously it's going to be less than what is greater than 10. Very simple mathematics. Okay. Now, keep checking till you find that, okay, it is not breaking any laws. So I know that now for 5, again check the parent. Now the parent is 8. Is 8 greater than 5? Yes, it is. Swap again. 8, 5 will be swapped. Now check with the parent again. Now the parent is 7. Is 7 greater than 5? Yes, it is. Okay, again swap. And now I can't go any more above. So done. That's it. Problem solved. How easy was that? This is known as up heap method. And since you know I'm only checking it once every level, only like once every level, I started like this, then this, then this. So 1 every level, and total how many levels we have? Log of n. So complexity is O of log n to insert an element. Easy. Sounds good? That's how you insert elements in a heap. Very simple. Try running it, pen and paper. Now let's look at how to remove elements. Okay, now removing an item from heap. This is actually very easy. I'm not enjoying, I want to teach graphs and dynamic programming. Heaps is too easy. If someone gives you a question, like this is the tree given and remove an element and make sure this condition is already satisfied, you can do it because you've done the binary trees videos, tutorials. I would say pause this video and think about it. Question is, if you remove an item, so you all understand how to insert an item? Well, let's say we remove the item in the min heap. So obviously the first item, this will be removed. Now, how do you rebalance this tree? How do you make sure that the next smallest item comes on top? How do you make sure we do that? Pause this and think about it. Okay. So you know how when we inserted, we just did like from the bottom to the up. This way we will do opposite. So just what you have to do is take the last element, because that I can get very easily because it's just at the last, and put it at the 0th index or the first index, whatever the first index is. Remove this, put it here, 10. Now search for downwards. So start from here, check what is smaller, left or right. You can get left easily, right easily. 2 into I and 2 into I plus 1. Okay. Initially I is equal to, let's say, 1. You can take I 0 as well. Maybe when I code, I will take array from 0. Not a problem. That will be simple. Very simple. What will be the values then? If you take array, like what will be the parent? Parent will be, instead of index divided by 2, index minus 1 divided by 2. Left will be index into 2 plus 1. And right will be index into 2 plus 2. Whatever, you can take from index number 1 also. Okay. So I'll check. Left is smaller or right is smaller? Left is smaller, swap it. Now from again, check here. Do I have to check it from here now for 9 as well? No, I do not. I don't have to check with 9. Okay, because of these conditions. Same reason as I gave previously. Similarly, now for 10, is left smaller or right smaller? Left is smaller, again swap. This will also be, this will be 7, this will be 10, this will be 8. Now left and right, there is no right, so I will not check, otherwise it will give me exception. Right, so there is no right. Left, is left smaller than the current value that I'm checking? No, it's not. Okay, program over, that's done. That's it. This is also doing the same thing, taking it only one at a time. That's why removing will also take log of n. Okay, insertion removal done. We saw the dry run as well. Try coding it. Try to code it. It's very simple. I just told you everything. Told you all the formulas. Try coding it from, let's say if we store it from 0th index itself. And instead of using array to make your life simpler, use array list. Array list is fine. Use array list. And very simple. Yeah. So log and insertion, log and deletion, we checked that. We saw the structure, how it's represented. We saw how the tree is represented using these formulas. Or you can start from 0th index as well. You can calculate formulas for that. I'll write it in the code. Code links can be found in the description below. I will be coding on the browser, so you can directly run it on your web page as well. So the link to the code is in the description. Is anything else remaining? No. Nothing else is remaining. Now it's just simple coding part. Coding part is simple. Most of my videos, the coding part is just 5 minutes. Simple. Okay, after this we will do heap sort and priority queue in this video only. Heap sort is nothing. Okay, heap sort is easy. I'll tell you right now. So it's so simple. Every time you are removing an item, you know that in min heap you are removing the smallest item. Okay, if I remove an item from here right now, it will remove 7, then it will remove 8, then it will remove 9, then it will remove 10, then 11, then 12, then 13, then 14. So keep removing items from the heap and just store it in a link, in an array list or a list, whatever you want to do. So n items if you remove, it will take n into log n time. N log n heap. That's heap sort. Heap sort is easy. Nothing in heap sort. Okay. I don't know what you want me to tell you. I feel like it, when I'm teaching, because I've taught in person as well. And I'm like, it's that simple. And people get confused. They're like, are you sure, Kunal bhaiya? Are you sure that it's just this and nothing else needs to be done? Yes, what else do you want me to say? What else can I say? Anything else remaining, any doubt you may have? No, you don't have any doubt. You feel like you have, but you don't. Nothing else is remaining. These topics are really easy. Don't worry about it. In data structures, algorithms, interview preparation, I said this many times, only 2 topics are challenging: graphs and dynamic programming. Rest, everything is easy. Hash maps, heaps, linked list, recursion, trees, stacks and queues, object-oriented programming, strings, arrays, everything is easy. Heap sort also easy. While heap is not empty, keep removing elements. That is heap sort. What else do you want me to say? We know removing 1 item is log n. So removing n item in n log n, heap sort complexity n log n. What else do you want me to say? Isn't that what heap sort is? That's it. Okay, these things are very easy. Please don't waste your time. So let's code it. I did the dry run. I explained everything. Time complexity done. Code example done. We just saw this dry run, how it works. And yeah, let's just code it. Okay, so here in my folder, by the way, you can check out the link in the description below. I'm just going to create new Java. I'm going to call this heaps lecture 1. I can just say heaps 1. Public create. Easy. All right, new file. I'm going to call it heap.java. And that's it. Class heap. Gonna zoom in a little bit. Okay, what do we do? This is how we do this. What do? We need array. So import java.util.arraylist and class heap is something we have over here. Okay, not a problem. What I'm gonna do is that I'm gonna make this of type like I'm gonna make it generic. Okay, so for example, you know what generics are, right? So if I say something like in the heap here, if I say something like, let's say heap of what? Heap of integer. Heap is equal to new heap. We all know what this thing is, the generics. We have done it in object-oriented programming. So here I will have to then make this also in terms of generics. There you go. Gonna say type T extends comparable. We all know how this thing works because we have done object-oriented programming. If you have not, please watch object-oriented programming playlist. This is how we can compare two objects. This is why I'm extending it with comparable, so I can compare two objects. Please understand. Okay. All right. That looks fine. Okay. Now heap will have an array. I'll just make an array list. Private array list of type T list. Constructor. Done. What now? Okay, but since we are going to swap a lot of elements, let's say this is an array list. I need to swap two indices, so I'll just create a swap function to make my life easy. Private, not returning anything. First index, second index. Temp is equal to list dot get first, list dot should be curly braces. Okay, then I can say list dot set. You all know how to swap two numbers, right? In an array, two indices. Please. If you don't know how to swap two indices in an array list, how can you clear your interviews? Please. And then list dot set. It is going to be very shameful for you if I explain to you how this method is working, this function is working. Question is swap two indices in an array list. It is going to be shameful if right now at this point of course I explain to you how this method is working. Shameful for you. That is why I'm not explaining this. So simple. No words. So watch the array list videos if you have any questions about this thing. Okay, imagine I teach you dynamic programming and you're like, Kunal, what does it mean by base condition in recursion? Does it make any sense? Shameful. You're learning dynamic programming and you don't know what recursion base condition means. That's shameful. Problem is not dynamic programming. Problem is you don't know recursion. So okay, fundamental should be clear. Now, another things I need is these thing: root, parent, root I know, never mind, parent, left and right. In this example I have, if root is equal to I is equal to 1, if I put I is equal to 0, so I minus 1, so parent will become, if I is equal to 0 means I minus 1, 0 will be what? Minus 1 for 0. So I'll just put minus 1 over here. So I minus 1 divided by 2, parent. Private int parent for this index will be return I divided by 2. I in reality is what? I minus 1 because we are taking it as 0. So I'm just taking index number 0 only. I'm not taking from index number 1. So minus 1. So just put minus 1 here. I minus 1 divided by 2. Okay. Not a problem. Similarly, left of this index will be what? 2 into I minus 1. No, not I minus 1. See about it. This is 0, 1, 2, 3, 4, 5, 6, 7, 8. Left here is 7. 3 into 2 plus 1. 1 into 2 plus 1. 0 into 2 plus 1. 2 into 2 plus 1. So I into 2 plus 1. Index into 2 plus 1. That's it. You actually don't need this because of the rules of basic mathematics. What is the right element? Index into 2 plus 2. Very simple. 2 into 2 plus 2, 6. 1 into 2 plus 2, 4. 3 into 2 plus 2, 8. 0 into 2 plus 2, 2. That is it. That is it. Now, insert of type T. I will insert a value in it. How do we insert? Remember, think about it. What did we do? So when you're inserting, first we will put the element at the last element, last index, not a problem. List.add value. So this will add it at the last. After this, I will try to swap it from bottom to above. This is actually called up heap. Up heap because I'm going up from the last index. Call up heap from the last index. Last index is what? List.size minus 1. Okay, I will now create up heap. So private void up heap int index. So what am I going to do? I'm going to check for the parent, get the parent. Int p is equal to parent of this index. But also if you are at the base condition, so if you're at the 0th index, then it is over. Then just return, nothing else needs to be done. Start checking for the parent. So if I added stuff over here, I'll check for the parent. Is parent, greater than the current value? So current item dot compare to parent should be less than 0. Means if the current item is smaller than parent, then swap. So if list dot get index, if item at this index compare to list dot get parent, means if this item is smaller than parent, swap index and parent. So it will be swapped, and then the new element that I'm going to check for is the parent index. So I'm just going to call the same function again with p. That's it. Easy. Simple. I showed you the dry run in this example as well. Very easy. Okay. Similarly, you can make remove. This will throw an exception because if you remove from an empty heap, if list is empty, removing from an empty heap, not cool. So how do we remove? Remove the item at the 0th index. List.get 0th index, and this temp will be returned. But swap the last element. I had the last element at the very 0th index, at the very first. That's what we did. Last is equal to list dot remove list dot size -1, and after removing this element I can say that if list is not empty, list dot set at the 0th index the last element, because it may be possible that heap only has one item. So when you remove this last item, you can see this is not actually removing it, this is just getting the value. Okay, after you have done that, it will be like, okay, now do the same thing you did from bottom to up, now do it from up to bottom. So down heap, starting from 0th index. Let's make down heap. Down heap is very easy. Okay, so down heap is what? Current index you are at, imagine that is the minimum. Get the left and right and see which one is minimum and then swap. I am not even writing any new logic, I am just writing it in code, whatever I taught you. Now in left and right, see which one is minimum. First of all, if left exists, so for example, if left is actually less than list.size and list.get minimum dot compare to list.get left, if this is actually, let's say, if the current min that you have assumed, which is, let's say we are over here, if this is actually greater than the left one, so more than 0, then min is going to be equal to left. This is also something I should not be teaching you. It's very easy. Don't be like, Kunal, oh, you are assuming that we know everything. No, shame on you if you think that this is something that needs to be explained. This compare to and stuff. I spent hours in object-oriented programming teaching you this. Then same thing in linked list, we also learned about compare to and everything. Okay. If right is less than list.size and compare to list.get, if right is greater than 0, means if the right element is greater than the min, then min is equal to right. In the end, you will have the min value will be equal to the minimum of current, left and right. So if min is not equal to index, means that you have found that either left or right, one of those is smaller than the current item. In that case, swap and call down heap in that swapped element. So if it was 8 and 7 over here, I swapped the 7 for 8 here, and then I will call it for 2. Okay, whatever the min index is. So I will say swap min and index and then I will just call down heap on that min, whatever min is. It will not execute if you cannot find something that is smaller than either left or right. In that case, our tree is nice, good. That is it. That's heap. Very simple. Not a problem. Okay. Very cool. Heapsort. Heapsort is very easy. Heapsort is a joke. I don't even feel like picking up my pen and paper and explaining it. Heapsort is simple. You have a heap. Till the heap is empty, keep removing items and put it in a list. First, it will remove 7. Okay, 7 will be removed. Then it will remove 8. 8 will come over here. Then it will remove 9. 9 will come over here. Then it will remove 10. 10 will come over here. Then it will remove 11. 11 will come over here. So you can see it is forming a sorted list. Every item removed takes log n time. Total, you will remove n items, n log n. Heap sort. That's heap sort. Heap sort. Can you do heap sort on your own? Very easy. Public, let's say I remove it in an array list of type T. Heap sort throws exception. Array list of type T. I can say list, or I can say data is equal to new array list. While list is not empty. While my list is not empty, just keep removing items from the list and add it in data. Please don't ask me what this keyword is. I will lose my mind. That's it. Keep removing till the list becomes empty. O of n log n. How simple is this? Is it not simple? Okay. Okay. Now I can add stuff in it. It's fine. Heap dot insert. If I say 34 or whatever, let's say it's min heap. So 45, 22, 89 and 76. And then I'm like, okay, remove item from it. System.out.println heap.remove. It should remove the smallest item, which is 22. Oh, so it should be, okay, yeah, throws exception. Because it's throwing exception, so should be declared. 22 removed, simple. What is the next will be removed? 34, then 45, simple. 34, 45, see, 34, 45. So easy. Instead, also one more thing you can do is heap sort. Array list is equal to heap dot heap sort. This will just give me the sorted list and log in. Heap sort. So many typos. Oh, java.import. I did not import. This import should work now. Ta-da! Heapsort easy. Time complexity done, how it works done, everything done, Heapsort done. This is also what is known as priority queue. Same thing. Okay. You can also make priority queue with linked list if you want. It's also very simple. But that's how the priority queue also works. Priority queue basically means it's a priority. Like my priority is I want to get the lowest item. So I will just use min heap. That's a priority queue. It's exactly the same thing. That's it. Max heap, another type of priority queue in which my priority is maximum items. Priority queue done. That's it. Okay, so that's what priority queue is. Now you'll be like, Kunal, what do you mean that's what priority queue is? Are you just going to teach us priority queue in literally just 10 seconds and say that is what priority queue is? Exactly. What we just did, that is priority queue. My priority is, let's say, minimum item, so it will give me minimum item. We did priority queue in this example using heap. That's it. Nothing else I need to tell you that is different. That is priority queue only. But you can also do it using linked list. So for example, you can insert it using a linked list. So you can maintain it using a linked list. Let's say I insert 3 first. Then I insert 4. Then I insert 8. So let's say minimum priority. So minimum item should be at the at the very first head of the linked list over here. Then I have 18. Then I want to insert, let's say, 10. So if I want to insert 10, I will check till which item, till which pointer is it less than 10. So it's going to be like till here it is less than 10. Okay. Go to this pointer by traversing one by one, obviously, because you cannot jump on an index in linked list. Watch the linked list playlist. Okay. So you cannot directly jump. So I will check from here. Is 3 less than 10? Yes, it is. Okay. Check again. Is 4 less than 10? Yes. Is 8 less than 10? Yes. Is 18 less than 10? No. So take the previous one, 8. Put it after this. This is how I am maintaining my priority queue. Problem here is inserting is taking O of n time. Priority queue, linked list. Not good. So we will keep using heaps. This is not important. Not good. Linked list one. O of n. No. Heap is doing the same thing. No, O of log n. So we will not use this one. I won't even code this because we don't have to use it. But you can code it yourself. It's very simple. Okay. So that's it. Okay, one more thing I want to teach you, then we'll wrap up and we'll do a question in the next video, questions. Okay, so let me teach you one thing. Let's say you're given this question. Let's say we learn how to create the heaps and everything, but let's say you're given an unsorted array and you have to create a max heap from that. Unsorted array is given. Let's say you're given 4, 1, 3, 2, 16, 9, 10, 14, 8 and 7. Remember the fundamentals, we have done the fundamentals. Indices, let's say I start with 1. 1 index, 2, 3, 4, 5, 6, 7, 8, 9, 10. Unsorted array given. Create a max heap from this. Initially, what will it look like? It will look like this. 4, 1, 3, 2, 16, 9, 10, 14, 8 and 7. It will look like this. Now the question is, create a max heap from this. What is max heap property? Every node should be greater than equal to all the children below it. So just try to do that for every single node. That's it. That is it. So for 7, every node below 7 should be greater than equal to 7. There is no node below 7 because it's leaf node. For 8 and for 14. So can I just skip these leaf nodes? Yes, I can. I can just skip these. these as well. I can skip these. I will directly start from 16. So (16) is what? Index number 5. Notice that this index by chance came out to be n divided by 2, 10 divided by 2, 5. That's not by chance. You know this property of complete binary tree. You know this property of complete binary tree. Why? Why are we starting from n divided by 2? You know this property of complete binary tree. Because we are ignoring all the leaf nodes, and the number of leaf nodes in complete binary tree is equal to what? It's around n divided by 2. So why start from n by 2? Because we know we are skipping all the leaf nodes, but we also know n by 2 plus 1 till n. So 6, 7, 8, 9, 10 in a complete binary tree all are leaf nodes. I'll be like, Kunal, how? How can you prove this? Well, watch the tree playlist, tree video. So start from 5 and then just call down heap on it for every single element. Okay, so obviously I don't have to check the leaf node because there's nothing to check. So for every node from, let's say, 5 till the root node, so 5, 4, 3, 2, 1 indexes, means for index is equal to n by 2 till 1, do down heap of that index and question solved. For 5 index, do down heap. For 4, do down heap. Why? Because that's what a max heap is. Every node is actually greater than equal to all of its children. But if I ask you the time complexity of this, what will it be? Outer loop is running n by 2 times. Inside it is calling down heap. Down heap is what? Log of n. We know that. So it will be n by 2 log n. But this is actually wrong. That's not the time complexity. We'll be like, Kunal, how? It is pretty clear from the formula. Just like with our analysis over here. It is not n by 2 log n. Sorry, n log n. It is not n log n. Then what is it? Let's see. This is going to be a little tricky, but I'll try to explain. For all the nodes that are in level, let's say, 1 above the leaf node, do you know that down heap is taking constant time because there's only one swap? For example, for this one and this one, there's only one swap. So constant time. Okay. And we know that one level above. So if I know that leaf nodes is equal to n by 2, one level above leaf nodes is equal to what? At level number 1. Number of leaf nodes again divided by 2. That's the property of complete binary tree. So n by 4. Level 1. Level 2 will have n by 4 divided by 2, n by 8. Level 3 will have n by 8 divided by 2, n by 16. Similarly, root level will have just 1. Okay. For the leaf nodes, the number of comparisons is 0 time. For one above the level, it is taking, let's say, some constant amount of time c. For level number 2, it is taking, now it is level number 2, so it is just 2 above, so 2 into c. This is taking 3 into c. Similarly, for the very last one, it is going to be taking what? How many levels into c? So root level is how many levels in the root? Log of n. So log of n into c. Okay. So what is the total amount of time? N by 4 into c plus n by 8 into 2c plus n by 16 into 3c plus 1 into log nc. So total time comes out to be n divided by 4 into c plus n divided by 8 into 2c plus n divided by 16 into 3c plus 1 into log n c into log n. Okay, if I just put n by 4 is equal to 2 raised to power k, it will give me what? It will give me, if I just take c common, because I can take c common from everywhere here, take c common, it will be 2 raised to power k plus 1 upon 2 raised to power 0. c 2 raised to power k I can actually take common. Cn by 4. Cn by 4 common. So this will be 1 plus 1 plus what? This is actually also 4. This is also again 1 plus 3 common. Actually let me not just remove it because it will make things confusing. N by 8 2. So I will just take 1 common, then I will take 2 common here, divide by, if I remove 4, 2 raised to power 1 or 2 raised to power 0 plus 3 common 2 raised to power 2 plus 4 common 2 raised to power 3 plus in the end I will say 2 raised to power k because it is log of n. So log of n is equal to what? Two raised to power k, just the same thing. So if this is 3, then here I can see this is 3 plus 1 4, 2 2 plus 1 3, 1 1 plus 1, so k plus 1. Simple. Okay. Now what I want you to see is that this thing over here, this thing is bounded by a constant. If you take 11th 12th mathematics, I won't teach 11th 12th mathematics, but this is actually formula sum of x I x raised to power I to infinity is equal to what? X divided by 1 minus x squared. So sums in mathematics, if you want to check that. Okay, it's divided by a constant. So hence this actually becomes a constant. This actually becomes a constant. So my time complexity is O of 2 raised to power k, which is equal to O of n. So it is not O of n log n, it is O of n. That was a little confusing, but I think if I dive too much into the mathematics, it's also something they won't ask you in your interviews that much because it's too heavily focused on maths. But just wanted to mention that a little bit. But yeah, it's very simple. You can use the functions that I have created, just run it in a for loop and just do this thing. Yeah, for I is equal to n by 2 till 1, call down heap on I, that's it. You can make that on your own. I can just literally say what it will be written like. But that's pretty much about it and very easy stuff. Very cool. Alright, so that was heaps made easy. We started with why heaps. We learned about how it's structured. We learned about the internal details, made it from scratch, ran it, learned about heapsort, priority queue, how you can do priority queue with linked list. Saw a nice example and we covered everything. Time complexity and stuff, demo, trial run, everything. In the next video, we will be doing some questions on heaps. These are free videos and free courses I'm making. If you want to support me, the easiest way to do it is like and comment, which you can do right now. And if you want to go above and beyond, you can take a screenshot, share it on socials using hashtag DSA with Kunal. I would really appreciate it. Most people don't do it because work required. You take screenshot, post it on social media, what you learned. That's okay, I understand. But if you can just like and comment, That's more than enough. And subscribe, like, comment, subscribe. Just takes 5 seconds. I'm saying this because that way it will motivate me more to create free courses for many people. And that's pretty much about it. So that was easy. Next videos we'll do hash maps, then some nice questions on heaps and hash maps, and popular topics like sliding window and stuff. But yeah, very excited. Heap is a topic which is important for coding interviews. So important questions. It's very important to see what type of questions are asked in which heap will be used. And as always, we look at the patterns. I teach you how to think and all sorts of things. So we're not going to do 100 questions, but using just 30 questions or something, I will tell you how to solve any heap problem, any other hash map problem, DP, or whatever graphs you want to do in the future. But thanks a lot for watching, and if you have any questions, leave those in the comment section below. Make sure you like, share, subscribe, comment, and I'll see you in the next one. Have a great day.